Hey everyone, and welcome to Cryogenic Engineering, brought to you by Bryson Knott, Ryan Leahy, and Rishi Nair.
Let's go through the basics of what cryogenic engineering is. It is the science and technology associated with generation of low temperature below 123 Kelvin. It comes from the Greek word cryo, which means very cold, and genic, which means to produce. Many technological advancements rely on cryogenic to function. We'll give more examples later on in the presentation.
So let's talk about the beginning of cryogenic engineering. In 1877, Cayete was the first to produce liquid oxygen using a cascade of pre-cooling baths. And on the same day that he achieved this, Pictet used a similar technique to achieve the same thing, but instead of using pre-cooling baths, he used vapor compression cycles. In 1895, Hampson replaced the cascade of pre-cooling baths with a recuperative heat exchanger, and then in 1902, Claude was able to liquefy air by using a reciprocating engine, which allowed a fraction of the high-pressure air to expand and cool before entering the low-pressure side of the heat exchanger. And details on these cycles are to come in the next couple slides. So here's a schematic of the cycle used by Hampson. The oxygen is compressed, passes through an aftercooler, which is a type of heat exchanger, and then passes through another heat exchanger, which exchanges heat with the oxygen flowing through the other side, then passes through a Joule-Thomson valve where it expands and cools. And then the liquid oxygen condenses near the evaporator, and whatever doesn't condense into a liquid passes through the evaporator and continues through the cycle. Here's a schematic of the Claude cycle, very similar to the cycle Hampson used, except it uses multiple heat exchangers and an expansion engine, which functions like a turbine. This setup allows for the compressed air to be used at a lower pressure. For comparison, the Claude cycle compresses the air to 2.5 megapascals, whereas the Hampson cycle compresses to a pressure of 20 megapascals, which requires significantly more power input to the compressor.
A lot of you might be wondering, how do we achieve such low temperatures? And that is done by using applications such as cryocoolers. Some of the refrigeration cycles that are used in cryocoolers include Stirling, Pulse Tube, Gifford, McMahon, Joule-Thomson, and the reverse Brayton cycle. And just like we learned in class with vapor compression cycles and cascade cycles, intercoolers are also linked together to achieve the lowest temperatures. Let's go in depth into the different refrigeration cycles. We'll start by talking about Stirling and the Guilford-McMahon cycles. Stirling coolers are one of the most widely used cryo refrigerator types for small remote and aerospace application. It consists of a compressor, a regenerator, and a cold displacer. So the way it works is the working fluid, which is typically helium, is compressed and the heat of the compressor is removed to the room temperature. Next, the compressor and the displacer move together to transport the helium through the regenerator, where the cold regenerator cools the helium. Then the displacer moves and reduces the pressure on the cold helium, which further cools the helium. At this stage, the helium absorbs this heat from the item which is being cooled and stays at a constant temperature. Finally, the displacer and the compressor move together to move the cold helium back towards the regenerator, where the helium cools the regenerator and warms back up to the initial state and close the cycle. The GM cycle is essentially the same, except in this design, a valve connects the high and the low pressure side of the compressor. This valve allows the speed of the displacer to be decoupled from the speed of the compressor. This means that the different engineers don't have to use custom-built compressors. They can just use a reliable and an inexpensive compressor, which makes it a more cost-efficient cycle.
Moving on with the pulse tube refrigeration device. This is unlike ordinary vapor compression cycles, it uses oscillatory compression and expansion of gas for intention of cooling. This technology is relatively new, which is invented in the 1960s. One key takeaway advantage is it does not have any moving parts at the cold end, which reduces those vibrations, or at the cold end, which increases the reliability and lifetime. Components are shown below. The main component the regenerator, the heart of the system, is described as a matrix of a porous media having high heat capacity and low conductivity to exchange the heat with the gas. Some quick applications for space in cryogenics. The cryogenic rocket engine, which uses liquid oxygen, hydrogen, and methane. Once combusted, they have a high efficiency and performance. Cryogenics is used to cool infrared sensors and telescopes that usually operate around 100 Kelvin. Also, cryogenics used for cryoelectronics in spacecraft, such as the metal oxide semiconductor integrated circuit, and also the SQUID superconducting quantum interference device. Some challenges for future development in the future of cryogenics for space is implementing these systems that are constrained by flight requirements for space travel.
The medical applications of cryogenics include cryosurgery and cryotherapy. Cryosurgery is a technique in which harmful tissues are destroyed by freezing them to cryogenic temperatures. It is used to remove things like cancer cells and molds. Some of the benefits of using this technique is that it leads to shorter hospital stays, less blood loss, and smaller recovery time. And then the second application that we talked about, cryotherapy, it is also called as the cold therapy, which is a local and general use of low temperature in medical therapy. It leads to, once again, quicker recovery time, reduced inflammation, improved joint function, and a lot more benefits.
Due to time constraints, we will not be going through the next couple of slides in detail, but the information is available to you if you are interested.
Here are some of our resources. Thank you for listening.